Now that we know what a subset and a superset and cardinality of set is, we can go on and define some set operations. So the first one we want to look at is the union of two sets. Okay, so the union of two sets A and B is the set of everything contained by either A or B. So what we say is if the element is in A, or it's in B, or it's in both, it's part of the union of A and B. Okay? So mathematically, we write it as a U without the tail, but this is the symbol for union. And let's use set builder notation to define this. Okay? So the union of A and B contains all elements X such that X is an element of A or it's an element of B. Okay? Instead of writing or, we could also use the disjunction symbol, but we'll talk more about that when we get to propositional logic in the following lecture. So for now, I'll leave it as or. Let's draw a picture. If this circle represents the set A and this circle represents the set B, the union is everything covered by either set. Okay? And so a good question is, how do we determine the cardinality of the union? Well, we'll get to that in just a second. But for now, this is all we care about for the union. So to show an example, if A is the set 1, 2, 3, and 4, and B is the set 3, 4, 5, and 6, the union of A and B is 1, 2, 3, 4, 5, and 6. We don't repeat 3 and 4 because, again, all we care about is unique elements. The next operation we care about is the intersection. Now, whereas the union contained everything that was in A or in B or in both, the intersection of two sets A and B is a set of everything that is contained only in both A and B. So to draw a picture again, if the left set is set A and the right set is set B, the intersection is right here. Everything contained by both. And the symbol for the intersection is an upside down U. So the symbol for union is a U. Union starts with U, that's how I like to remember it. And the symbol for intersection is an upside down U. And to write this in set builder notation, what we write is X is in the intersection if it's both in A and it's in B. Good. And again, as we'll see when we talk about propositional logic, before we wrote or with the disjunction symbol, here we can write and with the conjunction symbol. So that's a conjunction. It means and. But don't worry about that too much for now. To do a small example, we can say A, again, is the same set 1, 2, 3, and 4. B is the set 3, 4, 5, and 6. And the set of everything that's in both A and B is precisely the set 3, 4. Cool. So that's what the intersection of two sets is. So now, let's go back to the question, how do we determine the cardinality of the union of two sets? How do we determine that? Well, let's take a look. Let's draw our two circles again. Apologies for my terrible circles. We want to determine the number of elements that are in the union of A and B. Well, one good way to proceed is by first counting the number of elements in A and then counting the number of elements in B and seeing what we count. Okay? So if we first take a look at the cardinality of A, we count all of the elements that are in the A circle. It includes the intersection, but it also includes things that are not in the intersection. So that's cardinality of A. Then the next logical step would be to count the cardinality of B, or everything that's in B. Cool. And what do you notice? Well, we counted everything in the intersection twice, right? One time with the cardinality of A, and another time with the cardinality of B. But again, sets do not care about duplicates, right? we only want each unique element once. So that means we've counted the intersection twice, but we only want it to be counted once. So what we can do is subtract the cardinality of the intersection once. And this tells us the cardinality of the union of two sets. This is also known as the principle of inclusion-exclusion. And if you're following along with this course at UC Berkeley, you'll see that we have a homework problem where you determine the cardinality of the union of three sets. But even if you're not following along, this is a cool problem to work out on your own. Cool. Another interesting point regarding the intersection of two sets is that sometimes two sets don't have an intersection, right? So if A is 1, 2, 3, and B is 4, 5, 6, what is their intersection? Well, it's nothing, right? It's this empty set. Sometimes it's also written as a 0 with a line through it, okay? And if two sets have no elements in their intersection, we call them disjoint. Okay? So if the size of the intersection of two sets is 0, that means they share no elements. They're disjoint sets. Cool. So now we know what the intersection of two sets is, what the union is, and we determined how to find the cardinality of the union of two sets. The third operation we will look at is the difference of two sets. Okay? And so this is the first operation that we'll look at that is not symmetric. Okay? In that the difference of A and B is not the same as the difference of B and A. Here, the union of A and B is the same thing as the union of B and A, right? It's a set of everything contained in both. It doesn't really matter if you put B first or A first. Similarly, the intersection of A and B is the same as the intersection of B and A. It's the same thing, doesn't matter what order you arrange them in. But the difference of A and B is not the same as the difference of B and A. So all we care about is the set of everything that's in A but not in B. Best way we can look at this is by drawing a picture. If this is our set A and the right is our set B, the difference of A and B, it is what is over here. And the symbol we use for this, well, there's two. We could either use the minus sign or this backslash. Okay, and in a lot of mathematical text, this is what you'll see. In this class, we might use the top one a little more. Either one means the difference. To write it out with set builder notation, we say x is an element of the difference of A and B if x is in A and x is not in B. Okay, so that's what the difference of A and B is. One little problem or sort of misconception that sort of explains why we might want to use this notation for the difference as opposed to the minus sign is as follows. You might agree with me in that the union of A and B consists of three parts, right? It consists of the difference of A and B, which is this part right here. Difference of A and B, plus the difference of B and A, which is right here, plus the intersection of A and B, which is right here, intersection of A and B. But here I have negative B and positive B, so I can cancel those out. And here I have A and negative A, so I can cancel those out. And this implies that the union of A and B is equal to the intersection of A and B. So the question is, what just happened? And it's two things. One, well, really it's one thing. This addition symbol is not well defined in sets. We've only gone over three operations. The union, which is the U, the intersection, which is the upside down U, and the difference, right? So this addition is not really defined. So what we're doing here, like the addition is not the opposite of subtraction here. So that's why sometimes we get misled by using this minus sign. So instead, to make this valid, because this is clearly invalid, we'd have to write A minus B union B minus A union A intersect B. And that's perfectly valid. But to make it a little more clear, sometimes we like using the backslash notation. Cool, so A backslash B, B backslash A, and that's also valid. Cool. The last set operation we're going to look at is the Cartesian product. Okay, so we say the Cartesian product of two sets A and B is the set of all possible combinations of one element in A and one element in B. So there's not really a nice picture I can draw for this, but instead let me write out an example. Let's let set A be 1, 2, and 3, and set B be x, y, and z. Okay, so the Cartesian product of A and B will look something like 1 comma x, 2 comma x, 3 comma x, 1 comma y, 2 comma y, 3 comma y, and 3 comma x. Ooh, I'm doing this in the wrong order, aren't I? It doesn't matter. 1 comma z, 2 comma z, and 3 comma z. So this is every combination of one element in X and one element in A, and one element in B. Okay? So one question is the Cartesian product symmetric? And the answer is no. So each element of the Cartesian product is known as an ordered pair, right? And this is where we start getting into what a function is. So this is an ordered pair, okay? And the order of the elements in the ordered pair matters, right? 1 comma x is not the same as x comma 1. So what I can do is rearrange these ordered pairs, and that would still make the same set, right? So if I put, if I put 3 comma z here and put 1 comma x here, this is still the same set. But if I flipped the orders of all the elements in the ordered pairs, which is what would happen if I had B Cartesian product with A, those would not be the same thing. So the Cartesian product of A and B is not the Cartesian product of B and A. It's flipped. One way I like to think about this is the cross product when we talk about vectors. The cross product of A and B is the opposite of the cross product of B and A. So this is similar. Okay? So that's one way to think about it. And so the Cartesian product of B and A might look something like x comma 1, y comma 1, z comma 1, x comma 2, and so on and so forth, all the way till z comma 3. And again, the ordering of these pairs specifically doesn't matter. Like z comma 1 could come here, y comma 1 could go back there. Sets are not inherently ordered. Another question to answer is, what is the size or the cardinality of the Cartesian product of two sets? Well, since there's one pair for every combination of one element in A and one element in B, we can pretty easily see that the Cartesian product, the cardinality, of the Cartesian product is the product of the individual cardinalities. Cool, so the Cartesian product A and B, its cardinality is cardinality of A times card of B. Cool. So the last thing we want to talk about is what a universe is. So if we consider the example of talking about all of the students that are in this course at Berkeley, we need to provide some context, right? We need some larger set to compare the students in this class to. In that example, we used all of the students at Berkeley, right? So all of the students at Berkeley would be our universe. And the set of students in this class would be a subset of that universe. More specifically, a proper subset, right? And so what a universe is it is a set itself, but it represents all elements in consideration, all elements that we might care about for any one given problem. And so this is usually made clear to us when we're dealing with the problem, okay? So usually all sets are subsets of the universe we care about, and one thing we can define on any one given set is a complement, which is everything that is in the universe but not in a certain set. So for example, if our set A consists of the numbers 2, 4, 5, and 9, with our universe being the integers from 1 to 10, the complement of A is everything in the universe and not in A. Cool. So mathematically, you can write this as X such that X is not in A. We could also write it as the difference between the universe and A. So that's what a complement is. And this is something that we will study further when we talk about propositional logic. Okay? All of these operations, the complement, the union, and the intersection all have parallels when talking about propositional logic. The last thing we want to talk about when talking about set operations is what De Morgan's laws are. And so De Morgan's laws allow us to convert between unions and intersections, right? So it sort of goes both ways. So the first one says the complement of the union is the intersection of complements, okay? So the complement of A union B is equal to A complement intersect B complement. And the second one says the complement of an intersection is the union of the complements. Okay? So we'll work out the first one to show concretely that this works. And again, if you're following along with this course at Berkeley, this is one of the homework problems. But the second one is something you should work out on your own to show and convince yourself that it is true. So let's use an example of A being 1, 2, 3, 4, B being, let's make it a little bigger. 1, 2, 3, 4, 5, 6. B can be 2, 4, 6, 8, 10. And again, this is not enough because in any time we have a complement, we need to know what our universe is. So let's let our universe be 1, 2, 3, all the way to 10. Okay? Well, what's A union B? It's 1, 2, 3, 4, 5, 6, 8, and 10. 4, 5, 6, 8, and 10. What's the complement of the union of A and B? Well, it's all of the numbers from 1 to 10, all of the integers from 1 to 10, that are not in A union B. So that would be 7 and 9, I believe. Cool. So that's one thing. Now, let's individually calculate the complements of A and B and find out what their intersection is. Okay? We can do that over here. What's the complement of A? Well, it's 7, 8, 9, and 10. What's the complement of B? Well, it's all the odd numbers, so 1, 3, 5, 7, and 9. And what's the intersection of the two? Well, 1 is not in both of them, so it's not that. 3 is not in both of them, so it's not that. 5 is not in both of them, so it's not that. We see that there's 7 in both and 9 in both, okay? And lo and behold, what do we see? Well, we see that the complement of the union of A and B is equal to the intersection of the complements of A and B individually. In other words, this is of course not a proof because it only happened to work for this one example, but it's sort of an example showing to us and convincing to us that De Morgan's law, at least in the first case, is true. And again, a formal proof of this is something that you'll look at in homework, and we will also cover in discussion in this course. So that's all we need to talk about regarding set operations. And in the next article in the textbook, we will talk about what a function is in terms of all the things we've talked about regarding sets.